Hi there, this is Truth Socrates. Welcome to our video for today, where we will talk about the natural logarithm. Sometimes this is also called the natural logarithm function or the natural logarithmic function. So let's begin by saying, why are we going to study the natural logarithm? Okay, well, it's because of a missing formula in the power rule for integrals. Okay, so we know that the derivative of x to the k is k times x to the k minus 1 when k is a rational number. And we saw this in our last video where we talked about a brief history of the power rule. Okay, so the corresponding antiderivative formula is the integral of u to the n du is u to the n plus 1 over n plus 1. Okay, so yeah, it comes from this. If you divide both sides by k, then the derivative of x to the k over k is x to the k minus 1. So we'll get an antiderivative for x to the k minus 1. Replace k with n plus 1, and you will get this antiderivative formula. Now, we cannot divide by 0 ever. So n plus 1 cannot be 0, which means that n cannot be negative 1. So this means that we are missing a formula when n is negative 1. In other words, we do not have an antiderivative for u to the minus 1 du. Okay, and of course, u to the minus 1 can be rewritten as 1 over u. We don't have an integral for 1 over u. So that is what we are going to work for. All right, so next let me show you the game plan for this video and the next few videos. Okay, look back through calculus, through pre-calculus, before you took last semester's calculus class, where you usually start by looking at exponential functions. For example, 4 to the x or 2 to the x or 2/3 to the power x. Okay, if you might recall, 4 to the x is an increasing function, but 2/3 to the x is a decreasing function. Okay, and that's because 4 is a base which is bigger than 1, while 2/3 is a base which is smaller than 1, but still positive. Okay, so from here we usually talk about the natural number e, Euler's number e, which is approximately 2.71828, and using this as our base, we construct the natural exponential function. Okay, and all of them, whether it's increasing or decreasing, are one-to-one functions. So they have an inverse, which we call the logarithm to the base a of x. Okay, so for e to the x, the inverse of e to the x is called ln of x, the natural logarithm function. So natural logarithm NL, why is it LN? Well, part of it is tradition and part of it is language. Okay, so in this case, LN comes from the Latin translation for natural logarithm, which would be logarithmus naturalis. Okay, so LN, it's a natural abbreviation for the natural log function. Okay, however, we are no longer in pre-calculus, we are in calculus. And now we are going to go backwards. We will begin by creating ln of x. Then in the next video, we will construct e to the x. And then in the video after that, we will construct both a to the x and logarithm to the base a of x. So that is our game plan. Our first goal is to construct ln of x. All right, so in order to construct ln of x, we need to remember something you saw in first semester calculus, and that would be the fundamental theorem of calculus. The part that you probably remember is that if you're computing a definite integral, you look for an antiderivative for the function, for the integrand, and then you plug in the top number, and then you plug in the bottom number, and then you subtract the bottom value from the top value. Okay, we call them the upper limit or the lower limit. Okay, sometimes we just say the top number, the bottom number. Okay, but the part that you probably don't remember much is what leads to that formula. And it goes like this. Suppose you have a continuous function, f of x, on an interval I, and you pick a number a from that interval. Maybe it's an endpoint, okay? So I'm not saying that the interval is closed or open or anything like that. It's just an interval, okay? Then the function g of x, which is defined by this funny formula, g of x is the definite integral from a to x of f of t dt, where x is any other number from that interval, including possibly a. Then this function g of x is continuous on the interval and differentiable on the interior of I. Okay, so if you chose an endpoint for a, then you just ignore that endpoint and you focus on the interior of I. Furthermore, the derivative of g of x, in other words, g prime of x, is exactly the integral f, except it's not f of t. It's f of x, okay, the upper limit of that definite integral. Okay, so we are going, so yeah, you probably are wondering, okay, I don't remember this at all. Don't worry, we are going to go to GeoGebra in a couple of minutes where we will apply this to ln of x. All right, so this is how we are going to define the natural logarithm. We will apply the fundamental theorem to the function f of t, which is 1 over t. Okay, so we can't divide by 0. We will consider the domain from 0 to infinity. Okay, so this will be our interval I. Okay, we're supposed to pick one number from the interval. Our choice will be 1. Okay, so 1 is between 0 and infinity. So we will define the natural logarithm function, ln of x, to be the definite integral from 1 to x of 1 over t dt for any positive number x. Okay, so yeah, remember what the definite integral means. It is often interpreted as an area. But to be an area, we need to do a couple of things, okay? First of all, we should be going left to right, okay? So let's look at the case when x is bigger than 1, okay? In either case, 1 over t is always positive from 0 to infinity. If t is positive, 1 over t is also positive, okay? So therefore, when x is bigger than 1, this function represents the area bounded by 1 over t above the x-axis between 1 and x. Okay? We have a slight problem when x is less than 1. We're going the wrong way. Okay? We're going from 1 to 1/2, for example, if x is 1/2. Shouldn't we be going from 1/2 to 1? Well, we know that if we fix that, if we go instead from 1/2 to 1, we will have to put a negative sign in front of the definite integral, okay? But once again, 1 over t is still positive between 1/2 and 1, okay? So therefore, when x is smaller than 1, ln of x now represents the negative of the area bounded by 1 over t between x and 1, okay? So let's do instant gratification. According to the fundamental theorem, this is our g of x, this is our f of t, okay? G of x, f of t. The fundamental theorem said that the derivative of g of x, which is ln of x, is not f of t, but is f of x, okay? So instead of 1 over t, we plug in x for t, we get 1 over x. Okay, so there we go. The derivative of ln of x is 1 over x. So we can actually get an antiderivative formula from here. The antiderivative of 1 over x dx is the ln of x plus c. Okay, but that only works where x is positive. Okay, because that's how we define the ln of x function. Okay, so in a few minutes we will generalize that antiderivative formula, which I didn't even write down, to include the possibility that x is negative. Okay? And another piece of information we can get from this formula, if you plug in 1 for x, then you're integrating from 1 to 1, 1 over t dt. Okay, wait a minute. You're not going anywhere. You're going from 1 and you're going to 1. You are not going anywhere. Okay, so when that happens, we know from the definition of the definite integral that that integral is simply 0. Okay, so we have exactly one value. We know exactly one value for the logarithm function, and that is the ln of 1 is 0. That's all we know for now. All right, well, to see what our ln function looks like, let's try to get some sense using the definite integral. Okay, so our our f of t, we said is our 1 over t. Okay, so there it is. We all know what the reciprocal function looks like. Okay, but our g of x, our ln of x, is an integral from 1 to x. Okay, so we can actually ask GeoGebra to do a definite integral for us. Okay, so if we want ln of 2, for example, we will need to integrate from 1 to 2. Okay, so we will use the integral function. We will integrate 1 over, let's try 1 over t, from 1 to 2. Okay, does that work? Oh yeah, yes it does work. Okay, so GeoGebra is telling us that ln of 2 is approximately 0.693. Okay, so that is the value of ln of 2. It's not 1 over 2. Okay, it is this area from 1 to 2. Okay, but of course GeoGebra knows the ln function. Ln of 2, oh yeah, check it out. It's exactly the same number. Okay, so I'm going to plot that point. Okay, now that we know one other point on the graph, I'm going to plot 2, comma, 0.693. Okay, there it is. Okay. Oh, wait a minute. We know one other point. We said that when x is 1, ln of 1 is 0. Okay, so we have those 2 points. Okay. How about ln of 3? Okay, so I can change this number. Are you going to let me change that number? There we go. Let's go from 1 to 3. And now I get 1.0986. Okay, if I integrate from 1 to 3. Okay, so of course we're getting a bigger number because there is more area here that's going to be added to the area which we already had from 1 to 2. Okay, so we can plot that other point. 3, 1.09. Yeah, we'll just call it 1.099. Okay, there we go. Okay, so we have a third point in the ln function. Okay, let's jump over to 6. Okay, if we go to 6, hello. There you are. It's just a little slow today. Okay, 1.7917. So let's plot 6, 1.791. Yeah, sure, 17. Okay, there we go. So we're supposed to be connecting these dots. Okay, and those will be points on our ln function. Okay, now we said if our upper limit is smaller than 1, are we getting there? Are we there yet? Are we there yet? Let's just go to settings. Then we will change that to 1/2. Okay. And what are we going to get? Ooh, negative 0.693. Oh, wait a minute. We got 0.693 before. Now it's negative. Coincidence? Maybe, maybe not. Okay. So this time we will plot the point 1/2 and negative 0.693. Okay, so those 1, 2, 3, 4, I think there's one more there. 5 points will be strung together. Okay, let's try it for 1/3, okay? So it worked well for 3. Let's, for 2 rather, 2 and 1/2. How about 1/3, okay? What happens if we get minus 1.0986? Okay, this can't be a coincidence anymore. Something is going on here, and you probably know what it is if you remember your pre-calculus. 1/3 and negative 1.099. Okay, so that is another point on the graph of our ln function. Okay? So, you know what, let me hide this. Okay, there we go. So that we can see better the points on our graph. You can also move the labels. Did you know that? Okay, so there you go. They're a little bit out of the way now. Okay, so we are now going to ask GeoGebra to string these points together because, as I said, GeoGebra knows the ln function. Okay? So it will connect these dots together to form the graph. We can almost see it forming before our very eyes. And we can now hide where it came from, the 1/t function, where we were integrating. Okay? So now let's see. Can you graph ln of x for us? Ooh, there it is. Okay? So we are perfectly hitting those 5 points, even though they were just approximations. Close enough. Something's interesting happening here, though. It looks like we have a vertical asymptote for the ln function. And yeah, if you remember your pre-calculus, we are getting more and more negative, larger in absolute value. But on the other hand, here, as you move to the right, it is getting higher and higher. And are you going to get a local maximum or maybe a horizontal asymptote? We are going to find out next. Okay, so our next goals are to see what happens to the ln function as we go further and further to the right, to positive infinity, and as we go further and further left as we approach 0 coming from the right. Okay, so our ln of x function is defined only when x is positive. There's nothing on the left for now, at the very least. So we can only approach x equals 0 from the right. Okay, so we are going to work towards finding out what's happening over there by developing general properties of the ln function. Okay, so these are the properties that I was talking about. And we will call them arithmetic properties of logarithms because they involve arithmetic operations. Okay, so if a and b are positive numbers, because those are the only kinds that we can input into the logarithm function, and k is a rational number, then the ln of a times b is the same as the ln of a plus the ln of b. Okay, ln of a divided by b, on the other hand, is ln of a minus ln of b, and the ln of a raised to the power k, our rational number k, is k times ln of a. Okay, so you might be wondering, why does k have to be a rational number? Well, because to prove it, we're going to use the power rule for derivatives that we saw in our last video. Okay, so we will refer to these properties as the power rule, the quotient rule, and the product rule, the quotient rule, and the power rule for logarithms. Okay, so please note, while I'm thinking about it right now, there is no property for ln of a plus b or ln of a minus b. Okay, ln of a plus ln of b is not the same thing as ln of a plus b. Okay, there is no property at all which involves ln of a plus b. Okay, so if you plug in the special number a equals 1, then now we can explain what happened in GeoGebra. Ln of 1 over b is the same as ln of 1 minus ln of b, which is what I have here. But we know that ln of 1 is 0. So the ln of 1 over b is the negative of the ln of b. Okay, so we saw that when we had 1/2, we saw that ln of 1/2 looks a lot like the negative of ln of 2, and the same for 1/3. All right, so to prove the first equation, the product rule, we're going to use something from first semester calculus, and that is, if two functions have the same derivative on an open interval I, they can only be different by at most a constant. Okay, so in symbols, we say that if p prime and q prime are the same functions, then p and q are the same, except you are allowed to add a constant to the right side or the left side, as long as you add a constant to one of those sides. Okay, so let's warm up. If our p of x is ln of 2x, what is the derivative? Okay, so our p of x is ln of 2x. We want p prime of x. We said that the derivative of ln of x is 1 over x. Okay, but instead of x, we have 2x, so we have to put 2x in our denominator. But don't forget the chain rule. We need the derivative of 2x. Okay, so that is 2. We have to multiply our first answer by 2. Oh, and check it out. The 2's cancel, so we just simply get 1 over x. Wait a minute. That is the derivative of ln of x. Okay, so let's write that as ln prime of x. Okay, so this tells us that p of x and ln of x can only differ by a constant. Okay, so that works for 2. It doesn't take much to see that this will also work if the 2 is replaced by any positive number. Okay, so for this definition, we will get p prime of x will be 1 over 8 times x instead of 2x. And then we will multiply our answer there with the derivative of 8 times x, which is a. Yeah, there you go. The a's will also cancel. So we again get 1 over x, which is the derivative of ln of x. Okay, so according to our principle here, p of x, which we will generalize to this, will be exactly the same function of ln of x, except for a constant, a mysterious constant. Okay, so let's write that as thus. Ln of 8 times x is the same as ln of x plus a constant. Okay, so who is this constant? Well, we know exactly, we know the exact value of one number from 0 to infinity, and that is 1. Okay, so if you plug in x equals 1, plugging in x equals 1, we get, okay, so we'll get ln of 8 times 1, which is just a, equals ln of 1 plus c. Okay, but we know that ln of 1 is 0, so we will get 0 plus c, which is of course just simply c. Okay, so therefore our c is ln of a. Okay, so thus we can plug that into our formula. Ln of 8 times x is ln of x plus c. Our c is ln of a. Okay, and what are we trying to prove? Let's go back to our properties over here. We want to show that ln of a times b is ln of a plus ln of b. That is our goal. Okay, so let's come back over here. Are we close to our goal? I would say so. We have ln of a here, ln of a times x here. So it looks like all we have to do now is change x to b. So ln of a times b is the same as ln of b plus ln of a. But of course, we can exchange the order. Whoops. We can exchange the order of ln of b and ln of a. We just get ln of a times plus ln of b. Okay, so from property 1, it doesn't take much to prove the second property. In property 1, we can use the special case where, let's suppose that a equals 1 over b. Okay, so if b is a positive number, then 1 over b is also a positive number. So we can apply that in that formula. So we will replace a with 1 over b in that formula. So a is now 1 over b. A is 1 over b. Okay, but wait a minute, 1 over b times b is just 1. Okay, so I will put that on the other side. That is simply 1. Okay, wait a minute. We know what ln of 1 is. It's just 0. Okay, so this tells us that ln of 1 over b must be the negative of ln of b. Okay, and again, that's exactly what we observed in GeoGebra. The ln of 1/2 is the negative of the ln of 2. Okay, so now we can, prove this formula in general. So we can rewrite ln of AB. We can rewrite it as ln of A times 1 over B. Okay, so let me borrow the symbols here, and I will change B into 1 over B. Okay, so according to property 1, we can write this as ln of A plus ln of 1 over B. Okay, so pardon my construction here. Okay, there we go. Ln of A times B is the same as ln of A plus ln of 1 over B. But we just said that ln of 1 over B is minus ln of B. All right, so we get ln of A minus ln of B. Okay, so for the third property, we are going to go back to first principles like we did in the first property, and we're going to leave this to you for an exercise. Okay, so instead of what did we have, ln of A times x, we are going to look at ln of x to the power k. Right, so apply the derivative formula. Don't forget the chain rule. We had the times a earlier, and compare it to the derivative of this other function q of x, which is k times ln of x. Okay, so the power rule says that you can drop that k, and it looks like that is what happened over there. Okay, so you'll do the same thing. You will show that these two functions have the same derivative, so they can only differ by a constant. Find that constant, and that will show you that the third property is true. All right, now that we have these three properties, we can work our way towards proving what we said about the graph of ln of x when we were in GeoGebra. We have a vertical asymptote as x approaches 0 coming from the right. And as we go to infinity, is there a horizontal asymptote? Is there a local maximum? We're going to find out exactly what's going on over there. It's not as obvious as we can see about this vertical asymptote at the y-axis. Okay, so let's recap what we know so far. We said that the derivative of ln of x is 1 over x, but x is always positive in our domain, so 1 over x is still positive. And by the first derivative test in basic calculus, ln of x must be an increasing function. Okay, so it's always going up. And we saw that in the graph. Okay, it's kind of going like this. Okay, and it passes through 1, 0. Okay, so that's the only point that we know on the graph, for sure. So that tells us that because our function is increasing, ln of x must be negative if x is between 0 and 1, and ln of x must be positive if x is bigger than 1. Okay, now what about the second derivative? Okay, so the first derivative is 1 over x. Second derivative, power rule, that's x to the minus 1. Drop the power, so minus 1. Subtract 1 from minus 1, and we get minus 2, not 0. Okay, so the second derivative is negative 1 over x squared. 1 over x squared is always positive, so we get a negative second derivative. So by the second derivative test, our function is concave down, and we saw that. Okay, it's curving down like this. Okay, so let's go to infinity, the part which was not at all obvious from GeoGebra. Okay, what is ln? The idea is, okay, instead of going to infinity, let's just look someplace nearby. How about ln of 8? Okay, well, I chose 8 because 8 is a perfect power of 2. Okay, and according to the third property, which you will prove as an exercise, we can write this as 3 times ln of 2. Okay, and you might say, okay, big deal, but remember that ln of 2, it was about 0.69 something. Okay, so 3 times that, okay, fine, you get 2 point something. Okay, now, what if we made that 8 bigger? Okay, so instead of 2 to the third power, we did 2 to the 1000. Okay, that just got a lot bigger. 2 to the 10th power is already 1,000, 24, something like that. 2 to the 1,000, that's an enormous number. I don't even want to plug in that number into my maple here. But by the same idea, this is 1,000 ln of 2. Okay, and again, ln of 2 is just 0.69. Okay, so 1,000 ln of 2, that's actually not a very big number. Yeah, it's about 693. Okay, so do you see what's going on here? If I add another 0 here, this will just move to the right by another decimal point. Okay, keep adding zeros here. This decimal point will just keep moving to the right. Okay, so I hope you would agree. This shows that the limit as x approaches infinity of ln of x is positive infinity. Okay, we can make this number keep getting bigger and bigger and bigger. Okay, so now what about the limit as we approach 0 coming from the right? Okay, so in order to do that, we are going to do a little trick. Okay, so as x approaches 0 from the right, its reciprocal 1 over x approaches infinity. Okay, so what we're going to do is we're going to do a little substitution trick. All right, here we go. So we're going to let u be 1 over x. Okay, our substitution over here. So if you want x, it's simply the reciprocal 1 over u. Okay, they are reciprocals of each other. Okay, we are not going to do a derivative though. We are going to find a limit. Okay, so we want this limit as x goes to positive infinity. So we're going to start changing. As x approaches as x approaches 0 from the right, we said that 1 over x is approaching infinity. Okay, so our u will be approaching positive infinity. Okay, so I need to change this to plus, and I have infinity up there in my symbol panel. Okay, but we are not dealing with x anymore. We're dealing with 1 over u. X is 1 over u. Okay, well, we said a minute ago that the ln of the reciprocal 1 over u is the negative of the ln of u. Okay, so we can change this now to the negative of the ln of u. Okay, and that negative is a constant, so we can take it out of the limit sign. We can put it as -1 out here. Okay, so just so it's a little bit clearer. Okay, but we already said that as u goes to infinity, ln of u also goes to infinity. But we have infinity times -1, so it looks like we are just approaching negative infinity. So let me put that infinity symbol there. Okay, so that confirms what we saw in GeoGebra, that it does look like as we approach 0 from the right, our y is going lower and lower and lower. We have a vertical asymptote, which happens to be x equals 0, or the y-axis. Okay, so that clears up those two things that we were wondering about in the graph of ln of x. We can now introduce a very special number e, and again, we use the letter e in tribute for Euler. It's sometimes said that the greatest tribute you can pay to a mathematician is to use the lowercase of the first letter of their name. So there we go, lowercase e. Okay, so what do we have so far? Our function is monotonic increasing, and as you go approaching 0 from the right, you're diving down to minus infinity. But as you're going to the right, as x goes to positive infinity, ln of x is also going to positive infinity. Okay, so that means that you're hitting every number from minus infinity to positive infinity. Okay, so do you remember the intermediate value theorem? There is exactly one number e so that ln of e is 1. Okay, and that is why exactly one number? Because our function is monotonic increasing from 0 to infinity. So therefore, you cannot hit the same number twice. You cannot have the same y value twice. Okay, so let's go back to GeoGebra and let's see exactly where does e go in our graph over there. And we're back. Okay, so here's what I was saying. Our function, or ln of x, goes to minus infinity here. It will go to plus infinity here, but you're going to have to wait a long time because as we saw, even if you plug in 2 to the 1,000, its ln is only 600 something. Okay, so you're barely, you're not even 1,000. Okay, so where does e belong? We said we want the number e so that the y coordinate is 1. Okay, so 1 is over there, so e is going to be somewhere here. And as we said in the introduction, it's about 2.7. Okay, so we're going to type in the point e comma 1. Okay, there it is. Okay, it would have been nicer if it was the capital letter E, but no, it's okay. So that x coordinate is our e, which is about 2.718. Okay, if you want to see the point on the x-axis, sure. Okay, there you go. Okay, so the point G is exactly above the point H. Okay, so that x coordinate is about 2.718. That's the number E. All right, so far we can only find the logarithm of a positive number. What about negative numbers? Okay, so we're going to cheat a little bit, and we're not going to say that ln of negative 3 is the same as ln of 3. No, we're just going to say that we are going to compose the absolute value function with the ln function. Okay, so before you plug in x into ln of x, take its absolute value. Okay. Now, of course, absolute value can be written as it's either x if x is positive, or it's negative x if x is negative. Oops, there's a little mistake here, don't you think? We cannot plug in 0 into the ln function. Okay, so we have to change these as well. Okay, so what is the derivative of this composition? Well, we can do it piece by piece. Right? So we want the derivative of ln of x or the derivative of ln of minus x. Okay, and this should look familiar. The derivative of ln of x we know is directly 1 over x if x is positive. But if we have a minus here, we need the chain rule. Okay, so we have 1 over minus x multiplied by the derivative of minus x, which is minus 1. And once again, remember what happened, a times a, except there, a had to be positive. Okay, here we are allowing negative 1 because x is negative. Okay, so you cannot plug in x directly into ln, but you can plug in minus x. Okay, so again, the minus 1's cancel, and we get 1 over x, whether x is positive or negative. So in other words, the derivative of this ln of absolute value of x is always 1 over x, as long as x is not 0. Okay, so this tells us that the derivative of ln of absolute value of x is 1 over x, and so the corresponding full-bodied antiderivative formula is the antiderivative of 1 over x is the ln of absolute value of x plus c. And as usual, we are going to write our antiderivative formula in terms of u instead of x, because almost all the time we are going to need a substitution in order to apply this formula. Okay, so we're going to look at some examples. We're going to start with this guy over here. We want a definite integral from 5 to 8 of 1 over 3 minus 2x dx. Okay, so first let's make sure we're not dividing by 0. The only point where this is 0 is when x is 3 over 2. Okay, 3 over 2 is to the left of 5, 1.5. So 1.5 is not found in this interval at all. Okay, so we're going to find that antiderivative, and we're going to be very specific. That's for later. We're going to want the answer in the form a plus b ln of c, where a, b, and c are either integers or rational numbers. Okay, don't give an approximation until you have found the exact answer. Okay, so we will need a u substitution. So let u be 3 minus 2x. Okay, our denominator, so that is our 1 over u. Okay, so our du is negative 2 dx, and as before, dx, solve for dx, it is negative 1 over 2 times du. Okay, shall we change the limits? Okay, so when x is 5, our u is, what is 3 minus 10? Oh no, it's negative 7. Ooh, I'm a little worried there. And when x equals 8, u must be 3 minus 16, negative 13. Ooh, they're both negatives. Okay, I'm definitely worried. Okay, well, we are now ready to change everything. The integral that we want is, so instead of 5, we're going to have negative 7. And instead of 8, we will have negative 13. And instead of 3 minus 2x, that is our u. And our dx is negative 1/2 du. So we're going to copy this over here. Okay. So, well, we can, as usual, take the negative outside. That's just a real number, a constant. And the rest is still there. Okay. And this is where the absolute value is very important. Okay. So you cannot plug in negative 13 directly into our ln function. You must take the absolute value. Okay, so you have negative 1/2 of ln of positive 13, take the absolute value, minus the ln of the absolute value of minus 7, which is positive 7. Okay, so that's our final answer, except they're asking, I'm asking, for an answer where there's only one ln. Okay, there are 2 ln's over here, but we have our arithmetic properties. So we can write ln of 13 minus ln of 7 to be the ln of 13 divided by 7. Okay, not 13 minus 7, it is 13 divided by 7. Okay, so that is an acceptable final answer according to what we are being asked for over here. All right, I have a follow-up problem. Instead of just 1 over 3 minus 2x, let's change the numerator to something more complicated. Let's make it 5x plus 7. Okay, so we're going to recycle some of our solution above. Okay, we will still let our u be 3 minus 2x. Okay, so we have our du, our dx, our changing of the limits, but we are now going to deal with the numerator. Okay, so what do you do with 5x plus 7? You can't just keep it around because everything else is in u. You cannot integrate until all the x's have been turned into u's. Okay, so what we do is we solve for x over here. So from u equals 3 minus 2x, solve for x. Okay, so our x, what are we going to do? Well, let's move the 2x to the left side, and on the right we'll get 3 minus u. And from here, x will be 1/2 of 3 minus u. 1/2 of 3 minus u. Okay, so from here, we can solve for 5x plus 7, our numerator. 5x plus 7 is 5 times 1/2 3 minus u. So let me change this to 5 over 2. There we go. So if you distribute that, we will get 15 over 2. And then we will subtract 5 over 2u. And then plus 7. So let's see, that's 14 plus 15 is 29. 29 over 2 minus 5 over 2u. Okay, so that is our numerator, and we can now plug that in to our integral. Okay, so 5 again is minus 7, and 8 becomes minus 13. 5x plus 7 is now 29 over 2 minus 5 over 2u. And 3 minus 2x is our u. And our dx is minus 1/2 du. Get the whole thing there. Okay. There we go. Okay. Now, again, we can take the minus 1/2 outside, and we will have this du. But before we can integrate that, whoops, that's our next problem. Before we can integrate that, we will need to expand. In other words, distribute this divided by u to the two terms. Okay, so we'll get 29 over 2u, or we can just write that as 29 times 1 over u. How about that? Okay, 29 times 1 over u. And then the minus 5/2 u over u, that will just be minus 5/2. Okay, so let's clean that up. That's just minus 5/2, and we should wrap this whole thing in parentheses. Okay, so 29 over 2 times 1 over u minus 5/2 by itself. That's just a constant. Okay, so we are ready to integrate. Okay, our antiderivative is 29 over 2 ln of absolute value of u. Okay, so let me put in the absolute values here. Okay, there we go. I had to dig up that symbol from my symbol bar. And we have a minus 5/2 of u. Okay, no absolute values. Okay, 5/2 is just a constant. Think of it as a separate integral. You just have a minus 5/2 u. Okay, so we are going from -7 to -13. Okay, so as before, for the first term, we are simply going to get ln of positive 13 minus ln of positive 7. So let's put parentheses here, but brackets. Minus ln of 7. Okay, but for the u, we don't take absolute values. So it's minus 13 minus minus plus 7. Okay, so something different for that term. Okay, and we're almost there. Oh, we already evaluated, so we can get rid of that. So now we get to simplify this as best as we can. So like before, we can combine these two into single logarithm by using the quotient rule. And that goes away. And this is just arithmetic. So negative 13 plus 7, that is minus 6, correct? Okay, minus 6 divided by 2 is minus 3. And then times 5, that's positive 15. Okay, do I trust myself? And yep, it's positive 15. Haha. So this simplifies to plus 15. Okay, there we go. So you can leave your answer like that, or if you really insist that we follow the format of what I'm asking you, I don't blame you. I did ask you to write it as a multiple of ln. So we have 4 here, and minus 15 over 2. Okay, so we can copy this over here, minus 15 over 2. Okay, there you go. So it looks like a plus b times an ln of c. All right, our next example is an antiderivative of trig, tangent. We know that the derivative of tangent is secant squared, but in first semester calculus, we do not have an antiderivative for tangent of x. We have for secant squared, we have for secant tangent, but not for tangent by itself. Okay? So of course, the idea is to write tangent as in terms of sine and cosine. So I hope you remember that tangent is the same as sine over cosine. Okay. So now we need 1 over u. Okay? Well, the obvious denominator here is cosine of x. Let's try that. Hopefully it'll work. Suppose that our u is cosine x. So we have our 1 over u there. But we need dx, so du is the negative of sine x dx. Okay. Now, usually we would solve for dx, but let me show you a better way to think about it. Okay. In this integral, we have accounted for the cosine of x, but we don't have sine of x and we don't have dx. Okay. In this case, though, they come together. Okay. So keep them together. And we have negative du is the same as sine of x dx. Okay, that's more natural. Okay, we don't just want sine of x, we don't just want dx, we want both of them. Okay, so might as well get both of them from this single, very simple expression. So we are ready. Our antiderivative is our cosine of x is our u. And the sine x dx is negative du. So I'm going to change the numerator to negative 1 du. Okay, sine x dx is negative du. I'll write it as negative 1 over u du. Okay, so as usual, we can take the minus out, and we have antiderivative of 1 over u. And we will need the ln formula. So this is the negative of the ln of absolute value. Need it again. All right, so there's my absolute values, and I need negative ln of u. We can put the plus c later. So we have to change the u back to cosine of x. Cosine of x. Now, that is technically finished. However, okay, remember the reciprocal rule. Okay, ln of 1 over b is negative of ln of b. Okay, so we have a negative there. I am going to apply the reciprocal rule. Okay, so I will put the negative inside as a power minus 1. Okay, but of course that power minus 1 can go inside the absolute value. So we will get the reciprocal of cosine x. Okay, so instead of cosine x, I will have 1 over cosine x. You go to the bottom. There you go. We get the ln of 1 over cosine x, okay? But the reciprocal of cosine is also known as the secant, right? So we can write this now as the ln of secant x plus c. Okay, so there you go. The antiderivative of tangent of x is, let's display it, is the ln of the absolute value of secant of x plus c. All right, so now we know what the antiderivative of the tangent function is. Cotangent is almost the same thing. You'll be doing that as an exercise. All right, in our last video, we did the inverse trigonometric functions, and we saw how to apply the integration formula involving the arctangent to find this antiderivative. Okay, so a quick review. This formula works only if that number is 1 beside the u squared. So we have to take that 9 out, and then now we see that 4x squared plus 9 is a perfect square of 2x plus 3. So that's our u substitution. Solve for du, solve for dx. Change, we now have 1/9, 1 over 1 plus u squared. Dx is 3/2 du. We can take out the 3/2. 3 cancel with 9, we get 1/6. And inverse tan, bring back u is 2x over 3. Okay, so what we're going to do is we are going to make this a little bit worse, just like we did to our ln, that 1 over 3 minus 2x example. We made the numerator a lot worse, okay? So we are going to change the numerator to, how about, what did we have there? Something like 5x plus 3, something like that. Okay, so not that it matters. We are again going to need this integral, but we also need the formula for ln. Okay, so why is that? Well, the logical way to attack this integral is to separate it. Okay, so our numerator has 2 terms. We can think of this antiderivative as being made up of 5x over 9 plus 4x squared and 3 over 9 plus 4x squared. Okay, sometimes this works, sometimes this doesn't. Okay, so in this case, it is going to work, okay, as we are about to see. This we already know, sort of, okay, because we have this example, and all we do is change the 1 to a 3. So we just copy this down and we multiply by 3. So, oh, convenient. 3 times 1 over 6, that's 1/2, okay? The first term, we don't quite know, okay, except we know how to do a u substitution, okay? So, for the first integral, let's check out the denominator. Okay, 9 plus 4x squared, make that our entire u. So let's copy this down. So our du is 9 goes away, 8x dx. And that is really, really good because we have x dx in our numerator. Okay, so remember when we did sine of x dx, okay? Same idea. I want dx, but I also want x. Well, they're already together here. So why are you going to separate them? That's cruel. So instead, keep them together. And this time, how about we put them on the left side? Okay, so our x dx is 1/8 du. Okay, you can write an equation either way that you want. Okay, so the first integral simplifies to, we have 5 5x dx, so that's 5/8 du. So let's put our integral sign here. We will have 5/8 du. And we have 1/9x squared, that is our 1/u. Okay, so don't forget the du. All right, we have everything. Double check. 5x dx, x dx is 1/8 du, so 5/8 du. 1/9 plus 4x squared, so that's our 1/u. All right, so we get, and it's peeking over here because I reserved it. Haha. So we have 5/8 ln of the absolute value of u for our first term. Okay, but we're not done because u came from x. For that term, u is 9 plus 4x squared. Okay, so we'll put that in here. But, hang on a second. X squared is always positive. You multiply that by 9, that stays positive. And multiply by 4, that stays positive. Add 9, that's positive. So do we really need the absolute values? Nope. We can write this as ln of just 9 plus 4x squared. Okay? If you get the absolute values, that's fine. Okay? You really should not be punished for it. Okay? It's still correct. Okay, so now we are ready to put them together. Okay, we separated them. Now we are going to assemble them. Okay, so we said it is this plus this. So our first term is 5/8 ln of 9 plus 4x squared. And our second term is 3 times this integral. Okay, so we have 3 times 1/6. That will be just 1/2. Okay, and all we need is a single constant for the both of them. Okay, so that is the antiderivative of our example. All right, so for our final topic, we are going to introduce the process of what is called logarithmic differentiation. Okay, so to find derivatives, we have sum, difference, product, quotient rule, chain rule, implicit differentiation. Logarithmic differentiation is yet another tool that we could use to find the derivative of some functions. Not all, okay? It is suited when your function involves products, quotients, or powers. Okay, so remember, we had rules, corresponding rules for these for the logarithm. We don't have a rule for sums or differences. Okay, so in this case, I'm giving you a function which has a quotient and a product and powers. Okay, so how are we going to do this? We will take the natural logarithm of both sides of the equation y equals f of x. Okay, we will expand the right side using the 3 arithmetic properties of the natural logarithm. And then we will take the derivative of both sides of that equation using implicit differentiation. Okay, so let's execute the plan. Y equals f of x. So y equals this function over here. Okay, now we are going to take the natural logarithm of both sides of this equation. Okay, so we get ln of y equals ln of this monster over here. Okay, but we are going to apply now, expand the right side using the properties. Okay, so we have a product rule, a quotient rule, and a power rule. We see all of those in here. Okay, so we have to dissect this function and apply those 3 rules one at a time in a proper sequence. Okay, I would suggest we do the quotient rule first. Okay, because look at the big picture. We have a numerator divided by another denominator. Okay, so this naturally presents itself for the quotient rule. So this is the ln of 7x minus 4 to the 3rd power minus the ln of the denominator. Thank goodness for cut and paste, right? Okay, there we go. Okay, now, oh, by the way, we are assuming that all the factors in this expression are positive. Okay? So now, we can apply the power rule over here. That's nice. And we can apply the product rule over here first. Okay? So I'm going to copy this part. And I will save that for the product rule here. Okay? So we said that we can apply the power rule here. I can drop the power 3. And we have 7x minus 4. I don't need double parentheses. Okay, so there we go. Okay. So now we need to expand the product that we see over here. That's the ln of something to the fourth plus the ln of the other factor. Okay? So the ln of the product becomes the sum of the two ln's, like so. Okay. Now, we can apply the power rule here, but this is also a power. So let us rewrite this, of course, as 3x minus 8 to the power 1/2. There we go. Okay. So we are ready to apply the power rule to both of these terms. At the same time, we can distribute the minus sign. Okay. So that minus is very dangerous. So be careful in our next step. We're going to get minus 3 ln of x minus 4. And then the 4 will drop down to ln of 2x plus 5. And we don't need those extra parentheses. And then you get another minus. And then the 1/2 will drop down. So I need a fraction 1/2. ln of 3x minus 8. Okay, so I'm going to copy that. There. Woo! Okay, there we go. So everything that we have done from here to here to here, those are the 3 properties of the logarithm. Okay, applied one step at a time. Okay, sometimes we did 2. Okay, so far we have not done any calculus. Okay, but just big picture. What we have here is ln of y. Okay, so let me make that perfectly clear. ln of y is this thing. Okay, so now we are ready for the final step, which is we will take the derivative of both sides of this equation with respect to x, and we will apply the chain rule both on the right side but also on the left side. Whenever we take the derivative, a derivative with respect to x, and our expression involves y, the chain rule tells us we have to apply the chain rule to get dy by dx. Okay? All right, so let's do this. On the left side, the derivative of ln of y is 1 over y. Chain rule, we will need dy by dx. dy by dx. Okay, great. Next, 3 ln of 7x minus 4. Okay, so 7x minus 4, we get the reciprocal. The 3 will stay out. 3 over 7x minus 4. And chain rule, we need to multiply by 7 times 7. Okay, next, minus 4. And then ln of 2x plus 5, the derivative is 1 over 2x plus 5. So let's write it as minus 4 over 2x plus 5 multiplied by 2. Okay? And third term, we will have minus 1/2, 1 over 3x minus 8, and then multiply by 3. Okay, and I think it would be nice if we would simplify the right side. with all of those constants. So we will get 21 in our first numerator. The 2's don't cancel. Minus 4 times 2, that's minus 8. Okay. And what to do with this guy? Well, I suppose we can promote it to the numerator. You can write it as 3 halves there. Okay? If you like, you can put 2 times 3x minus 8. Okay? Either way is fine. Okay. And we're almost finished, okay, because we want dy by dx. Okay, so we just isolate, we will isolate dy by dx, and we get dy by dx equals y times that entire mess on the right side. Okay, there you go. Okay, so that is just about finished, except there's a y over there. Okay, is it possible to have everything in terms of x? Well, yes, of course, because y is this, where it all started. So all we do is we replace y with that, and we will get that times this. Okay, that's our derivative. So can we leave it like this? Yeah, sure. For me, this is perfectly acceptable. You could distribute this to all 3 terms. Notice how some of the 7x minus 4 is going to cancel. Some of the 2x plus 5 is going to combine here. Some of the 3x minus 8 is going to combine there. But for me, this is a perfectly acceptable final antiderivative. Okay, so wow, that is my longest video so far. Thank you so much for your patience. I hope that you were pressing the pause button every now and then and maybe taking a little walk to the refrigerator or something. But in any case, thanks for watching this video, and I will see you next time. Enjoy the rest of your day.